Big Bang Nucleosynthesis. How the universe made its first atoms. Have you ever wondered where the atoms that make up everything around us came from? The answer lies in the very early universe, during a period known as Big Bang Nucleosynthesis, or BBN. BBN refers to the formation of the first atomic nuclei in the minutes following the Big Bang. It's a crucial cornerstone of the Big Bang theory itself. This process explains the observed abundance of light elements like hydrogen and helium in the cosmos. In fact, BBN provides some of the strongest evidence we have for the validity of the Big Bang theory. Imagine the universe just moments after its birth. It was an incredibly hot and dense soup of fundamental particles. This primordial soup contained quarks, leptons, and photons, all interacting at unimaginable energies. As the universe expanded and cooled, these particles began to interact in new ways. Quarks, for example, combined to form protons and neutrons, the building blocks of atomic nuclei. However, in the earliest moments, conditions were simply too energetic for these nuclei to remain stable. The era of Big Bang nucleosynthesis began approximately 1 second to 3 minutes after the Big Bang. By this point, the temperature had dropped to a point where nuclear fusion could occur. Protons and neutrons began to collide and fuse together, initiating the creation of the nuclei of the lightest elements. This was the universe's first act of alchemy. It was a period of rapid and intense nuclear activity, laying the foundation for the chemical composition of the universe we see today. The primary reaction in BBN was the fusion of a proton and a neutron to form deuterium, a heavy isotope of hydrogen. Deuterium acted as a crucial stepping stone for the creation of heavier elements. Further fusion reactions led to the formation of helium-3, another light isotope of helium. But the most abundant element produced during BBN was helium-4. In addition to hydrogen and helium isotopes, trace amounts of lithium-7 were also synthesized during this period. These light elements are the legacy of BBN. The rapid expansion of the universe played a crucial role in limiting the extent of BBN. As the universe expanded, its density and temperature decreased rapidly. This expansion eventually halted further fusion reactions. There was simply not enough time or energy to create heavier elements in significant quantities. Another key limitation was the lack of stable nuclei with a mass of 5 or 8. This gap in nuclear stability prevented the formation of heavier elements like carbon and oxygen during BBN. These heavier elements, essential for life as we know it, would have to wait for the formation of stars and the process of stellar nucleosynthesis. Despite its limitations, Big Bang nucleosynthesis is a remarkable success story. It accurately predicts the observed abundance of light elements in the universe. BBN predicts specific ratios of hydrogen, helium-4, helium-3, and lithium-7. These predictions align remarkably well with astronomical measurements. This agreement between theory and observation provides strong support for the Big Bang model. It confirms our understanding of the conditions and processes that occurred in the early universe. The success of BBN is a testament to the power of physics to explain the cosmos. It's a cornerstone of modern cosmology. Big Bang nucleosynthesis was the cosmic forge where the first atomic nuclei were created. It laid the foundation for the formation of stars, galaxies, and ultimately everything we see around us. Without BBN, the universe would be a very different place. It was essential for the formation of the complex structures we observe today. The story of BBN is a testament to the power of physics to unravel the mysteries of the universe. It's a remarkable story of the universe's beginning. It highlights how fundamental processes in the early universe shaped the cosmos we inhabit today. The elements forged in those first few minutes continue to influence the universe's evolution. So, the next time you look up at the stars, remember the Big Bang nucleosynthesis. Remember the cosmic forge that created the building blocks of our universe. Before we dive deeper into the reactions, let's paint a clearer picture of the early universe. Imagine a time when the universe was far smaller, hotter, and denser than anything we can comprehend today. This wasn't a void, but a seething soup of fundamental particles. Quarks, leptons like electrons and neutrinos, and photons were all crammed together in a state of extreme energy. The temperature was so high that atoms couldn't even exist. Any attempt to form a nucleus would be immediately disrupted by the intense heat and collisions. As the universe expanded, it began to cool. This cooling was crucial, as it allowed particles to combine and form more complex structures. Quarks, for instance, started to bind together to form protons and neutrons. These are the building blocks of atomic nuclei, and they would play a central role in BBN. The ratio of neutrons to protons in the early universe was a critical factor in determining the outcome of BBN. Initially, neutrons and protons were in thermal equilibrium, meaning they could readily convert into each other. However, as the universe cooled, this equilibrium began to break down. Neutrons are slightly heavier than protons, and it became energetically more favorable for protons to exist. This led to a gradual decrease in the neutron-to-proton ratio. By the time BBN began, there were significantly fewer neutrons than protons. This imbalance had a profound impact on the types and amounts of elements that could be formed. It's a delicate balance that shaped the universe's composition. The formation of deuterium was the first major hurdle in BBN. Deuterium, a heavy isotope of hydrogen, consists of one proton and one neutron. However, deuterium is relatively fragile. It can be easily broken apart by high-energy photons. In the early universe, there were plenty of these photons around. This created a deuterium bottleneck, preventing the formation of heavier elements until the temperature dropped sufficiently. Only when the universe cooled enough for deuterium to survive could BBN truly get underway. This delay had significant consequences for the final abundance of elements. Once deuterium formed, it quickly reacted with protons and neutrons to produce heavier elements, primarily helium-4. Helium-4 is an exceptionally stable nucleus, consisting of 2 protons and 2 neutrons. A vast majority of neutrons present in the early universe ended up bound in helium-4 nuclei. This explains why helium-4 is the second most abundant element in the universe, after hydrogen. The amount of helium-4 produced during BBN is remarkably sensitive to the expansion rate of the universe. This makes it a powerful tool for probing the conditions of the early cosmos. While BBN's predictions for hydrogen and helium are in excellent agreement with observations, there's a persistent discrepancy when it comes to lithium-7. Observations suggest that there is less lithium-7 in the universe than predicted by BBN. This is known as the lithium problem, and it remains an active area of research. Scientists are exploring various possible explanations, including uncertainties in nuclear reaction rates, the presence of exotic particles, or even modifications to the standard cosmological model. The lithium problem highlights the fact that our understanding of the early universe is not yet complete. It's a reminder that there are still mysteries to be solved. BBN produced the raw materials for the first stars. These stars, born from the primordial soup of hydrogen and helium, were vastly different from the stars we see today. They were much more massive and short-lived, and they played a crucial role in enriching the universe with heavier elements through stellar nucleosynthesis. This is the process by which stars fuse lighter elements into heavier ones in their cores. The heavier elements created in these first stars were then dispersed into the universe through supernova explosions. These elements became the building blocks for future generations of stars and planets. In essence, BBN laid the foundation for the entire cycle of stellar evolution and the creation of the elements that make up our world. Big Bang Nucleosynthesis is not just a confirmation of the Big Bang theory, it's also a powerful tool for probing new physics beyond the standard model. The abundance of light elements is sensitive to various cosmological parameters, such as the baryon density and the number of neutrino species. By comparing BBN predictions with observations, scientists can place constraints on these parameters and search for deviations from the standard model. For example, BBN can be used to constrain the properties of dark matter and dark energy. It can also be used to test theories of modified gravity and extra dimensions. In this way, BBN serves as a window into the very early universe and the fundamental laws of nature. Big Bang Nucleosynthesis is a remarkable achievement of modern cosmology. It provides a compelling explanation for the origin of the light elements and offers strong support for the Big Bang theory. It's a testament to the power of scientific inquiry and the ability of humans to understand the universe around us. The story of BBN is a story of discovery, innovation, and the relentless pursuit of knowledge. The elements forged in the first few minutes of the universe continue to shape the cosmos today. They are the building blocks of stars, planets, and ultimately life itself. So, the next time you look at a periodic table, remember the Big Bang nucleosynthesis. Remember the cosmic forge that created the elements that make up our world.